Hello and welcome to Argonne at Lunch. My name is Justin Bro, and I'm with Argonne's Media Relations and External Affairs Department. Argonne is one of 17 Department of Energy national laboratories. We're also managed by the University of Chicago. Now, you might see a sign right behind me. We're standing in front of the Nuclear Energy Exhibition Hall, and you're in for a real treat today. We're going to be speaking with Lydia Finney, who is the program initiator for Argonne's WIST program, the Women in Science and Technology program. We're also going to be speaking with Roger Blomquist, who's a nuclear engineer and former Navy captain. He's going to lead us through the past, the present, and the future of Argonne's nuclear engineering legacy. So let's go ahead and let's talk to Lydia. Hi, Lydia.
Hi, Justin.
How are you?
Great. Good to see you.
All right. So tell me a little bit about WIST. What is WIST?
WIST is the Women in Science and Technology program, which is a program of the Office of the Director at Argonne National Laboratory. And its purpose is to support and empower our women at all levels, both inside and outside the lab.
So you said outside the lab. So you bring groups from the outside inside the lab. Can you give me an examples?
Sure. So we have two events where we bring women in from outside the laboratory. The first is our Introduce a Girl to Engineering Day. In that event, we bring about 100 middle school girls in for a day at the laboratory. The other event is our Science Careers in Search of Women Day, where we bring about 300 high school girls and 100 of their teachers in to spend a day here at the laboratory.
That's wonderful. That's wonderful. Now, I understand before you became the program initiator for WIST, you were a physicist. So talk to me a little bit about how those two jobs are different.
Right. So I was a physicist at the Advanced Photon Source at Argonne National Lab, and my work there was really to discover new things in science and technology. On the other hand, the work that I'm doing now as the Women in Science and Technology Program Initiator is to help to empower our women scientists and engineers to do their work well.
That's amazing. That's amazing. All right. So is there anything else that you want me to tell me? Like, what is a twist tour? So I know a lot of our people that are watching right now, they might be maybe a little bit confused about what twist tour is. So you want to explain that a little bit?
Sure. The twist tours were started about 5 years ago by our WIST program, with the idea being that it's very easy to be here at the lab and to not even really know about a lot of the science that's going on right around you. So we wanted to give our own scientists and engineers, and it's open to both men and women at the laboratory, a chance to learn more about the research that's going on right around them.
That's wonderful. And about how many tours a year do you have? Because what we're about to see is one of those tours.
Right. So we do about 4 tours per year, and we try to do them over the lunch hour.
That's wonderful. That's wonderful. Well, thank you, Lydia. We're gonna start our tour right now. We're gonna speak to Roger Blomquist, who's a nuclear engineer and former Navy captain. And here he is. Hello, Roger. How are you?
Justin, just fine. How are you?
Excellent, excellent. So, for the viewing audience, Roger told me this pretty amazing story about being in the Navy and sleeping next to a nuclear reactor, and you'll do it much better justice than I could. So why don't you go ahead and tell me that story?
So, well, the submarine obviously is a sealed steel tube that's submerged. It's sealed to keep the water out. And there are about 100 and some people working on that ship, and they all pretty much sleep next to the reactor. In my case, my bunk was about 35 feet from the reactor itself.
Wow, wow. So that has, I'm sure, colored your ideas about nuclear engineering and nuclear power.
Well, it demonstrated for me the fact that this was a very, very clean technology when you could seal all those people up in one tube with a reactor and nobody gets contaminated or any kind of a radiation dose that matters.
That's amazing. That's wonderful. And so if you're just joining us, we're here at Argonne at Lunch. We're going to be doing a WIST twist tour of the Nuclear Energy Exhibition Hall. And we're speaking with Roger Blomquist right now. And Roger's going to lead us through. And to begin, we're going to start with Chicago Pile 1. So I'm going to let Roger take it from here. He's going to lead us on a tour. But let's go ahead.
Okay, Chicago Pile 1 was a physics experiment. It was part of the Manhattan Project. And the physics experiment the purpose was to demonstrate that a self-sustaining neutron chain reaction could be arranged and put together with the right materials. And they succeeded. And the Germans had a similar program. They ran into some technical difficulties and they had some political issues too. And but this was a race between the U.S. and Germany, and it was a race that we won. In terms of what it meant for the future, this was is like unleashing a new form of fire. So Initially, we started burning wood back in, thousands of years ago. So it was all renewable type energy. And then we discovered fossil fuels maybe about 200 years ago, and those replaced to a large extent the renewables. And now we have an even denser form of energy in uranium, and that is going to, in the future, I think, replace a lot of the fossil fuels. Uranium, if I fission one atom of uranium, it produces the same amount of energy as I would get if I burned 7.5 million molecules of natural gas.
So say that one more time, just so people get the idea.
Fission one atom of uranium, I get the same amount of energy as burning 7.5 million molecules of natural gas. And that gives you an idea of the amount of material that's required, the fuel material and waste material that goes into and comes out of any sort of fossil fuel generating plant.
That's amazing.
A nuclear system, the fuel is sealed up. When it goes in, it's still sealed up when it comes out. So it's very close to a completely closed system.
What I'm going to do is I'm going to ask Don to go in here just really quick while actually Don, come back. I want you to give me a nice look at all these people that are right behind us, because if you didn't already know, this is an actual tour. So these people are here to learn things about nuclear history and Argonne's nuclear present and nuclear future. So they're going to be joining us along with this tour. But what I'd like to have you do is walk on, once you're done here, walk on in here where we have wonderful historical artifacts that go back to Argonne's nuclear history, and we can continue our tour.
So there were 40-some, I think 49 people present on December 2nd, 1942, when this experiment was successfully completed. And there is, I think, one of them still alive. They all pretty much live normal lifespans. And we have here in the exhibit some artifacts. We have Enrico Fermi's immigration papers. And we've got a working Geiger counter with a source that people can play with. We have some sketches of the initial core, CP1 core, and a paper trace of the power during the approach to criticality. So that was Fermi's instrument, December 2nd, 1942. We also have some original graphite from CP1. And also, there's some over there in the corner you can actually touch. Graphite does not become radioactive in reactors. And we have a very nice model over here of the CP1 experiment, which was conducted in a squash court under the football stands at the University of Chicago.
So they did this experiment to understand and to get the criticality underneath the stack field. Is that correct?
That's right. Originally, the experiment was supposed to happen in the forest not too far from the laboratory here, but they had a lot of construction delays, and then there was a labor action. And rather than, since this was a top secret project, rather than lean on the parties in the labor dispute that would tip off somebody that this was something really, really important, they just moved it to the squash court. And squash court's kind of nice from a security point of view. It doesn't have any windows. And this is before electronic surveillance. So if you can control who comes in, who goes out, and what they're carrying, you've got good security.
So you might have any questions? Yeah, okay. Well, why don't we move on to understand that we're moving to commercial reactors.
Let's spend just a minute on the apple tree.
Okay.
So this apple tree is Argonne's nuclear genealogy. Argonne has designed, built, and operated 28 reactors, 14 here and about 14 in the deserts of Idaho at Argonne West. And the red apples were the ones that were designed, built, and operated by Argonne. The green ones were designed by Argonne but built and operated by somebody else, or in a few cases canceled. And so we begin with CP1. Then there's a research reactors branch, and one of these was a heavy water reactor, which the Canadians ended up commercializing as a can-do reactor, and they have sold dozens of these around the world. On this branch is kind of the submarine branch. So we did the initial physics experiments and core design for the USS Nautilus, and we did that in partnership with Westinghouse Corporation, and they took that technology and scaled it up for commercial use for electricity generation and commercialized it. And then we did a series of experiments in Idaho on boiling water reactors, and we ended up transferring that technology to General Electric Corporation, which has become the boiling water reactor company. So essentially all of the power-producing reactors in the world today stem from designs and experiments that were conducted at Argonne.
Now, I see this, and this is really cool. Actually, I'm sorry, I'm going to jump right in front of you. So you can come here, and you can come to this exhibition hall, and you can touch these, and you can find out the history if you just want to click on one of these. There you go. And it'll take you into the history of that particular reactor. But as I understand, this is also available on the website. So if people want to find out more, tell them where they can go.
It's www.ne for nuclear energy, .anl for Argonne National Laboratory.gov, G-O-V.
So yeah, that's where you can go to find out more information, especially see this mock-up of all, basically the history, and find out what's going on with nuclear reactors.
It's on the About tab on that page. So there's one more branch here, and we'll get to that in a few minutes. That's the fast neutron reactors, which have very special characteristics. And I hope by the end you'll understand what those are.
We will. Now we're going to move on to commercial reactors. Everyone follow us along.
So this is a model of a regular commercial reactor fuel assembly. This is not an Argonne reactor. This is more like what we have today operating in the United States and around the world. And if this were full size, it would be 12 feet tall. So this one's from a somewhat smaller reactor. But a reactor itself consists of a rack of these things packed together tightly in a cylindrical array, about 12 feet tall, about 12 feet in diameter for a 1,000 megawatt plant. And the reactor coolant gets pumped in the bottom and flows up along these tubes. And there is uranium dioxide, a ceramic material, in the tubes, and that's where the chain reaction is occurring. And basically, it's a pile of hot rocks that are organized in a way so that we can extract the heat and use it to produce energy and electricity, thermal energy and electricity. And this is the way all power-producing reactors work. And so make a note of the size of this thing, for in a minute we're going to get to what happens in a fast neutron reactor. So the way a commercial nuclear power plant works is this thing, or this rack of things, would be right here inside the reactor vessel, which is inside a heavy containment building. It's something like 4-foot thick steel reinforced concrete. And the reactor cooling system is inside this. So you can see here there's a pump pumping water in, and it flows up along the fuel pins, extracts the heat, goes to a heat exchanger called a steam generator. It's just like your car radiator, except your car radiator's got air on the outside and engine coolant on the inside. In this case, it's radioactive water, very hot water, very high pressure water that's boiling water, different non-radioactive water on the other side of the tube, and that is used to produce the steam, to turn the turbine and the generator to produce electricity. So a fossil fuel plant would be identical, except you'd have a big furnace here instead of the reactor building and the reactor. So this is a mature technology. And of course, you've seen these cooling towers. Other thermal plants use cooling towers like that too, the hyperbolic cooling tower. So when you see one of those, it's not necessarily a nuclear plant. Questions? Yeah.
Maybe this will be in the future. Are you eventually going to talk about the control rods and how they turn this thing on and spool it up and spool it down?
Sure. So, I'm glad you asked. Right here is another model which shows how the control rods work. So you can't touch this because it's delicate. It's made out of wood. But this is like a control rod hand at the end of a long steel rod, and this is how the control rods are moved in and out. So in this case, we would pull the control rods out, and there would be normally about 24 rods that fit into places where we've removed a fuel pin, so there's space for it. And so that's how it works, and there's a motor at the top that operates this. And they typically are, if you lose electrical power, then they fall in on their own. They don't need something to drive them in. So that's one of the inherent safe features of nuclear power plants.
So this is how you actually control the amount of energy that's coming out by lifting the rods up and down into this device?
Yeah, indirectly, what actually controls the amount of energy is how much steam you're producing from the reactor. When you start up, the control rods control the power level, but once you reach operating power, then it just controls the temperature of the reactor. So we just make minor adjustments. Right. So these control rods move very rarely, except during startup and shutdown. They move very rarely and in only small increments. So they aren't really a moving part. So a reactor itself has basically no moving parts in it. Like I said, it's a pile of hot rocks. It just sits there, and the rocks are hot, and the heat gets out, and it gets used to produce electricity. And what's in that fuel element I showed you over there in the corner, that's the way fresh fuel looks. It's also the way it looks when it comes out of the reactor. Each of those tubes, metal tubes, is welded shut. And so all the radioactive material that comes out of the fission is stuck inside of those tubes. So I think now I'd like to contrast fast neutron reactors with our current commercial reactors. So let's go over here to the other side.
And if you're just joining us, this is Argonne at Lunch. We are on a whist twist tour of the Nuclear Energy Exhibition Hall. We're speaking with Roger Blomquist, who is a nuclear engineer and former Navy captain. And we just spoke about commercial reactors. We're going to talk about fast neutron reactors right now. So let's listen in.
So we want these to be commercial reactors, and the Russians actually are operating 2 very large commercial plants of this type. This was an early experiment. This is 1951. At that time, it was thought that uranium was very scarce and that we would not have enough uranium to support a large-scale deployment of nuclear power in the U.S. or the world. And so there's a workaround for that. Natural uranium has got only 0.7% uranium-235, and that's the uranium isotope that fissions. Uranium-238 doesn't fission very much at all. But if it absorbs a neutron, eventually it becomes plutonium-239, and plutonium-239 in a reactor acts just like uranium-235. So it's a way of increasing the miles per gallon, so to speak, by a factor of 100. So, a factor of 100 that's a big resource extension. It turned out that we have a lot more uranium than we thought at the time, but this is still going to be a very good idea from a resource point of view. It makes it really sustainable. This is the actual size of that first reactor, and it was the very first reactor in the world to generate electricity. This is Argonne's reactor in the Idaho desert. So this stuff has been, the shielding and so forth has been cut away. These are the fuel pins. This is done with our 3D printer. And you can see the control rods here and so forth. So, the follow-on to that was experimental breeder reactor number 2, which was built in 1964. And I'd like you to contrast this fuel element with the one over there. Anybody care to point out a contrast? Size, it's a lot smaller. Now, that is sort of like 1,000 megawatt size. This one is 20 megawatt. But even if I scaled this up to 20 megawatt, it would be about 1 meter by 1 meter. So it would still be way smaller than a current commercial pressurized water reactor. How do we do that? We don't cool it with water. We cool it with liquid metal sodium, which is 100 times better at sucking heat out of pins than water is at those temperatures and pressures. So you don't need as much sodium. You can pack everything more tightly, and that has a lot of advantages from a variety of points of view.
I have a question. Are the materials that you're putting here smaller or no? They're about the same size.
The same mass of materials?
Right.
No, it's way less mass. Yeah. And these are the fuel pins. So this section here corresponds to that whole thing over there that we just looked at. So it's much more compact. So let me show you the inside of this reactor. So this is a pretty old model, but it's a beautiful one. Back when making models was real craftsmanship. It still is to a large extent. So one of the nice features about liquid metal sodium is when you heat it up to the temperatures that reactors experience, it's still atmospheric pressure. So for our commercial reactor over there, we need a pressure vessel that's 8 or 9 inches thick. It's got to hold 2,200 pounds per square inch pressure. That's 150 some atmospheres. That's a lot of pressure. And we do that just fine. I mean, our current reactors work very well. They're plenty safe, but it's expensive. And particularly the vessel is expensive. So you want to make it as small as possible, so it's not quite shrink wrapped around the core, but pretty close to the core. But that means you have to have the cooling system outside of it. So you have to weld nozzles and piping onto it. And that's also expensive and difficult. But we do that, but it makes it tougher to build and more expensive to build. Since we have a low pressure system here, and this is very similar to molten salt systems in that regard, we only need a vessel that's maybe 1 inch or 1.25 inches thick. That means it's way cheaper. That means we can afford to make a much bigger one. And in fact, we can make it so big that we can embed the entire reactor cooling system inside of that pool. This is why it's called a pool plant. And we can make it big enough that we can put enough sodium in there that if we lose electricity and we have to remove the excess heat that continues for a while after the chain reaction shuts down, we have enough thermal mass in there that it heats up very, very slowly. And in fact, if EBR-2 had been at Fukushima, they would have had 2 weeks to figure out how to get some cooling, additional cooling to it. The people at Fukushima had something like 45 minutes after the tsunami hit.
Wow.
So that's a huge improvement in safety. The other great thing about this reactor is it can be configured as a nuclear garbage disposal. So we could take, with some recycling, which we have demonstrated, the spent nuclear fuel from all of our light water reactors and convert what we haven't used, the energy content we haven't used, to electricity and short-lived nuclear waste. So everyone has heard about the Yucca Mountain repository. It's supposed to last for 300,000 years. That's because of the plutonium content, which has a very long half-life. This kind of reactor, because the neutrons are fast, it really changes the nuclear physics balances going on in there, and it fissions elements like plutonium very nicely and converts them to fission products with much shorter half-lives. So instead of 300,000 years, if we partition the materials and recycle as much as we can, we only need to build a facility that will last about 300 years. So that's a factor of 1,000 improvement in the period during which we have to protect this material. From a safety point of view, we did some very revolutionary experiments in Idaho in 1986, where we tried to break this reactor by turning off the cooling pumps at 100% power. We're not stupid. We obviously did a lot of analyses ahead of time, and we did a few low-power tests before just to make sure, but it was clear that this was going to work. And so, of course, we invited a lot of VIPs to this experiment, or demonstration, I should say. And so we put the VIPs right behind the reactor operators, who are going to be the guys turning off the pumps. And when they turned off the pumps, the VIPs turned around to see if the Argonne guys were still there or had they left the room. And they were still there. And the system demonstrated that it would shut down its chain reaction by itself without any control rods, and it would absorb the excess heat for a very, very long time. So it's a very robust system. And that comes from the low pressure characteristics of sodium and the excellent heat transfer characteristics. So the end state was just a natural circulation system that operates just the same forces that your chimney does, keeping the reactor cool enough.
A question? Sure.
I have a question because I don't really understand this, and I'm trying to. So we saw pictures of like the rock, and we saw the squares, I don't know what you called the graphite. So what is it when you put that in? What shape is it? You know, what kind of form? I've seen rods. What is the form that actually takes of the uranium when you put it in there?
So in CP1, which was a physics experiment, so it was operated at a very low power, so they didn't have to remove any heat. It just warmed up the room a degree or two. or something like that.
Like a rock form, or was it a rod, or what was it?
Those were big chunks of uranium or uranium dioxide. But you couldn't operate that at high power because it would be too hard to get the heat out fast enough. And that's why we use much smaller rods in our current commercial reactors and in fast neutron reactors. So the ability to remove heat depends on the distance the heat has to move through the material. So you could imagine a big, thick chunk. On average, it has a longer way to go. So that's why thin rods are pretty nice for extracting the heat. Is that?
Somewhat. I'm still trying to understand the whole process, but
Follow-up questions are welcome.
I know. Lydia's been very helpful in explaining it to me in Kathy terms, so.
Well, I think another question, though, that Kathy had was so you start up a new nuclear reactor, right? Like one of the commercial designs. And the fuel that you put in there, how long is that reactor going to keep running with that first batch of fuel?
Okay. So fuel stays in our current generation of commercial reactors for 5 to 6 years. And then it's taken out. It's uranium-235 is mostly used up, and it's full of the fission products that are the split-up uranium atoms. Many of those absorb neutrons, so it can't sustain a chain reaction anymore. That's why we call it spent fuel. Still has a lot of energy available in the non-fissioned uranium that's in there, and plutonium. A coal plant the same size as a 1,000-megawatt nuclear plant would require. Now that's basically a rail car load of fuel every 5 years. It's done more frequently than that, just partial reloads, but that's the overall balance. If I have a coal plant, I need a 100 rail car train every day. And obviously that material isn't accumulating inside the coal furnace. So the products have to go out. The products are CO2, sulfur and nitrous oxides, which are toxic and environmentally damaging, even heavy metals, including some uranium. So some of this comes out as gas, some of it comes out as fly ash, and the fly ash has a fairly high radioactivity content. If I run a gas plant, I put in a pipeline, so I dispense with the railroad. But still, it's a huge flow of gas coming in, and the products have to go out. In the case of methane, or natural gas, which burns pretty clean, that's mostly water vapor and CO2.
It's good.
We have a Facebook question.
It says, where is it stored? Where is it stored?
Facebook questions asking, where is the spent fuel stored?
So right now, at our commercial plants, the spent fuel is stored at the reactor sites. When it first comes out of the reactor, it still needs some cooling for about 5 years, so they're stored underwater in pools, large pools. And then after 5 years, it can be air-cooled, and in many cases, some of the older fuel has been taken out and put into dry cask storage above ground. Remember, this fuel can't sustain a chain reaction anymore, and after it's been out for 5 years, it still is hot to the touch, but it's not going to self-destruct because it's overheated.
Are there any other questions? All right. I think we can move on.
Okay.
If you're just joining us, this is Argonne at Lunch. My name is Justin Bro. We're speaking with Roger Blomquist, who's a nuclear engineer and former Navy captain. He is leading us through the Nuclear Energy Exhibit Hall here at Argonne National Laboratory. And we've moved just from the fast neutron reactors. We talked about commercial reactors before. We even talked about Chicago Pile 1, where the whole party began, where the atomic age was born. So we're going to move on from that to our next example.
So just before we do that, I'd like to point out we have a model here of the fuel recycle facility that we built in Idaho that was attached to EBR-2. So we were able to recycle fuel from EBR-2 through this system and back into EBR-2. So the technology's been demonstrated. The economics have much bigger error bars, but that's one of the things we're working on now, is trying to nail down the economics. So we have successfully, we call it closing the nuclear fuel cycle. And this is what enables you to increase your fuel economy by a factor of 100, the recycling.
Now, as we're moving on, I understand there is a conversion that goes on from nuclear reactors, and this is what we're going to talk about right here.
So, in the 1950s and 60s, during the Atoms for Peace era that President Eisenhower announced at the UN to encourage countries around the world to develop peaceful uses for nuclear energy, the U.S. and other countries gave away and sold large numbers of research reactors to countries and universities around the world. And research reactors are best operated with highly enriched uranium. So there was, and highly enriched uranium is one of the materials that you need for a nuclear weapon. So in the 1970s, it was realized that, maybe some of these places are not ideal for having highly enriched uranium. And so we started a program here at Argonne that was supported by the State Department and the Department of Energy to convert research reactors around the world from high enriched uranium to low enriched uranium. That involves a very multidisciplinary approach, as all of nuclear engineering is. We had to redesign cores, and we had to produce new fuels that had 5 to 10 times as much uranium per unit volume of fuel, which is a metallurgical or material science challenge. So, and we still have a program where we're still pushing the envelope on that further and further. There are about 250 research reactors around the world. We've converted 70 of them. Another 25 or 30 have been shut down. Others were fueled with low enriched uranium to begin with. We're now kind of down to the hard cases. They're either hard because of the international situations or because these are very high performance reactors that have much greater technical challenges. But I'd like to show you a model of one of these research reactors that we did convert. This is the Jamaica, it's called the Jamaica Slowpoke reactor, and it's a Canadian design, and the yellow-green pins are visible in the center, and the red blocks around the outside are the neutron reflectors that keep the neutrons from leaking out so that we can use them in experiments. So Jamaica uses this reactor for education and training, and you can see over here on your left side there's a gray thimble in which you can lower samples of materials, and this would typically be samples from river water in Jamaica, because Jamaica has our biggest business is export of bauxite, which is aluminum ore, and bauxite ore comes naturally with some heavy metal contamination. And so the government of Jamaica wanted to know if the heavy metals in their water supply were coming from the mining operation or were just part of natural runoff from the environment. And you can put a sample of that river water or its residue in here and irradiate it with neutrons, and radioactive materials give off sort of like a fingerprint that you can use to identify the exact radioisotopes. And so the government of Jamaica was able to find the source of this stuff and work with their regulators to get their water supply cleaned up. And they still use this for monitoring their water supply. So here's a reactor whose primary mission is environmental, not just energy production. And research reactors around the world are used for producing medical isotopes. They're used to produce industrial isotopes for food sterilization, radiographing welds in very thick vessels, and so forth and so on, and doing a lot of experiments that have helped out in the area of medicine and biology.
I just want to point out that, and I think we talked about this before we even started, this is the actual size of the reactor.
This is actual size.
So if you can remember what we were looking at before, these reactors were huge, of course, right? Like can you give us a numerical comparison about what this is to what we saw before, maybe in the fast neutron reactor?
I think this one is 20 kilowatts. I'm not sure. So that's 0.02 megawatts, and the ones I was talking about earlier were 1,000 megawatts. So it's much bigger. You need a bigger core to produce more energy. That's just the way it is.
But you can use this for experimental purposes.
Yeah.
And you can pretty much lift it up.
This doesn't have a cooling system. It doesn't need one. And it's not operated at 100% power all the time. When you have a commercial reactor, you want You want it generating electricity all the time because that's how they make money and supply electricity. So,
Now, do we have any other questions? Do we have any Facebook questions in? No. All right, so what I want to do is I want to bring in Lydia as we close out our conversation today. We're going to play Mythbusters, and hopefully that name is not copyrighted, so please don't sue me. Mythbusters, that's what we're going to do. So one of the things that we often hear about are these questions that people have or these things that people say about nuclear energy in particular that may not be true. So since we have a resident expert here, we're going to ask a couple of those questions. So my first one is, Americans get most of their yearly radiation dose from nuclear power plants. True or false?
false. Americans get the biggest part of their yearly radiation doses from medical diagnostics and procedures. In fact, a third of all medical procedures in the United States involve radiation.
One myth busted. A nuclear reactor can explode like a nuclear bomb. True or false?
False. A bomb requires highly enriched uranium. We don't put highly enriched uranium in reactors, so the uranium would have to somehow magically enrich itself in a system with no moving parts.
Which could probably happen at Hawkins' lab, my Stranger Things fans. Okay, so I have a question for Lydia here. What did you work on as a physicist?
The work that I did as a physicist was at the Advanced Photon Source doing X-ray fluorescence imaging. So one of the ways I can describe that to you is that we've taken samples and imaged them, things like the Tully monster fossil from the Field Museum, and we're able to see where iron is in the sample, where zinc is in the sample, and understand things that we didn't know before about the Tully monster.
Excellent. Nuclear energy is bad for the environment. True or false?
I just cite the submarine. You seal everybody up in the submarine and operate the reactor. It provides your fresh water, your oxygen, and everything else, and it's like it's an ecosystem.
Take this from the man that slept next to a nuclear reactor, and if you don't believe that, I don't know what to tell you. Why do women need their own group? So insofar as the Women in Science and Technology group, people may have the question, why do women need their own group at a national lab?
So one of the things that remains true about science and technology today is that it's still a male-dominated field. And because of that, it's helpful to our women to support and help them support each other in their work so they don't feel isolated.
Right. An American Chernobyl would kill thousands of people. True or false?
We don't now and never have built Chernobyl-type reactors in the United States. That accident was due to a design that basically caused the accident along with their egregious violation of their own operating procedures and safety principles.
So there you have it. So design flaw and egregiosity. I think I just made that word up, but that's fine. So that became false. All right, so I'm going to ask Lydia, this is our final question. What are the stats? How are we doing in terms of the numbers of women in science and in leadership? And you just covered that a little bit more than science is in general a male-dominated field. But do we have any numbers to back that up?
Yeah, so right now, in general, in tech, in science, women in the workforce is around 15-20% in R&D. We are seeing a lot of changes in terms of the number of women that are going into these fields and studying them in college, in graduate school. And some of it takes time, but some of it takes our continued efforts and encouragement, because we're all going to be better as a nation if we're putting all of the intelligent minds we have available to the task at hand.
And no doubt those programs like Science Careers in Search of Women and Introduce a Girl to Engineering Day, those types of programs help get young ladies at least interested in a future career in the STEM field, science, technology, engineering, and mathematics. So thank you. I want to thank Lydia Finney, Argonne's WIS program. I want to thank Roger Blomquist, nuclear engineer at Argonne National Laboratory. My name is Justin Bro. You stay classy, Argonne.